Hello, ladies and gentlemen. We're going to do 10.3 today. We're going to be talking about parametric equations in calculus. And no, there's not something wrong with the sound. I caught germs from my beloved grandchildren. Alrighty. So we are going to be finding the slope of a tangent line to a curve, and then we're going to find the arc length of a curve. So the first thing that we want to talk about is a parametric form of a derivative. So we've talked about derivatives in all types of forms before, so now we're going to talk about it in terms of parametric. So if I have a parametric set of equations, x is equal to f of t and y is equal to g of t, and I want to take the derivative, so dy dx is going to equal dy dt over dx dt. And basically that just means I'm going to take the derivative of my y parametric, and I'm going to take the derivative of my x parametric, clean it up, and we do have to make note that dx dt can't equal 0 because then the world would explode. Alrighty, I have a simple little example for us, super easy, because it's really not that complicated process until we start taking multiple derivatives. So let's say I want to find dy dx for the curve given by x is equal to the sine of t and y is equal to the cosine of t. Well, again, I'm just going to take, because I have a system of parametric equations, I'm going to take the derivative of the y thing, and I'm going to take the derivative of the x thing. Alrighty, so my dy dx is going to equal dy dt divided by dx dt. So my derivative of cosine is a negative sine, and the derivative of sine is the cosine of t, and then this turns out to be a negative tangent of t. Well, that was pretty easy. The next thing we need to talk about are higher order derivatives. Alright, so just like with all of our other functions that we've talked about, I want to be able to talk about concavity, and I need to be able to find the second derivative then. Okay, so then this is going to be the derivative of dy dx, which no duh, and then this is d dt, because we're dealing with parametric equations, of dy dx divided by, I'm going to put that little guy in brackets, dx dt. Alrighty, and this is just going to be something that you're going to have to memorize, because I think that will just make this process easier. So you're going to take the derivative of dy dx, and then you're going to divide it by dx dt. And if you'll notice, you're going to get your dx's cancel, and it's going to clean out and be really polite. If, for some reason, you needed to take yet another derivative, okay, then you would have d dx of the second derivative, that one goes there, dx squared. Then this one would be d dt of the second derivative, d2y over dx squared. And once again, I would divide by dx dt. So I don't know that you need to memorize the whole process, but this is actually pretty easy to memorize, because you'll notice that the numerator is just going to be the derivative of the previous derivative, and then I'm going to divide by dx dt. Alrighty, so let's do an example. Okay, so we're going to have a curve, and it's going to be x is equal to the square root of t, and y is going to equal 1/4 t squared minus 4, and t is going to be greater than or equal to 0. And I want to find the slope and concavity at the point 2, 3. Alright, So since we're going to find the slope, first derivative, then we're going to find the concavity, second derivative. So that's actually not too difficult, okay? Sorry, feel like I'm dying. All right, so if I want to find the first derivative so that I can talk about the slope, that's going to be the derivative of the y thing divided by the derivative of the x thing, highly technical term. So if I take the derivative of my y thing, here's the 1/4, here's the 2, t to the 1, and then the 4 would go away because it's a constant anyway, so I don't have to distribute. And then the derivative of my x thing is going to be 1/2 t to the negative 1/2. And I'm going to let you clean up this algebra because I'm sure you're brilliant. And so when I do that, I get t to the 3/2. All right, so I wanted to find the slope at the point 2, 3, but my 2 is in terms of x, so I need to find a value for t. So I'm going to go to another sheet of paper, okay? So I'm going to write that my dy dx was t to the 3/2, okay? And since I had x is equal to the square root of t, sorry, I'm going to square both sides, so square and square, and I'm going to get t is equal to x squared. Well, if my x is 2, then my time is going to equal 2 squared, which is 4. Alrighty, then my dy dx, my slope at the point 2, 3 is going to equal 4 raised to the 3/2, which is the square root of 4 raised to the third, and so that's going to be 8. So if I report my answer nicely, my dy dx at the point 2, 3, that's going to equal 8. Alrighty, so the next thing I want to do, and I'll change to a different color just because, so it's the second part of the problem. I want to find the second derivative, okay? So dx squared, well, the equation for this, and I'll rewrite it since we just learned it, is the derivative of my dy dx divided by my dx dt, okay? So if I take the derivative of my dy dx, it's going to be 3/2 t, and then 3/2 minus 2/2 to the 1/2, and then I have to go back to my dx dt, which was the 1/2 t to the negative 1/2, and you have that in your notes, so I didn't rewrite it, and we had found this previously. So if you do this math, because you're brilliant, then you would get 3t. So then the problem was to find I guess it's our task, was to find the concavity at the point 2, 3. So my d2y over dx squared evaluated at the point 2, 3 is going to equal 3 times 4. Remember, the 4 is our t, and then that's going to give me 12, which is positive or greater than 0, which means that we have concave up. So at the point 2, 3, my system of equations is concave up. Alright, so that was actually a fairly simple example. Alright, let's do another example along these lines. Okay, and this one is, before we do that, I guess I'm going to stop for a moment. I'm going to give you a little factoid, which I thought was entertaining that your book called it a factoid. So let's say I have f is some function of t, and y is some function of t. Okay, it doesn't have to be y as a function of x. Okay, it is also possible for plane curves, so I'm going to write possible for plane curves. Remember, that means a two-dimensional curve to loop around. Okay, and so if the graph loops around, it might have more than one tangent at a given point. We'll get to the example in just a sec. So, since you can't see what I just wrote, all right, so what that might look like is, let's say I have this cool graph. So here's my graph, and I'm going to have this cool figure 8 kind of thing. And then I might die in the process. Okay, so this point is actually not at the origin, so I just made a big dot. But if you'll notice, I have a tangent going that way. I'll get a different color, and I have a tangent going that way. So we'll call this guy tangent 1, and we'll call this guy tangent 2. Okay, so this particular guy is called a prolate cycloid. That's a weird word. We've had lots of weird words in this chapter. Okay, and his particular set of equations is x is 2t minus pi sine t, and y is equal to 2 minus pi cosine t. You remember, if you want to look at these, you can put them in your calculator. You need to be in parametric mode, and you also need to be in radians. Alrighty, so we're going to continue with this problem, and I want to find the equations of both tangent lines at the point 0, 2. So like I said, I drew that kind of at the origin, but I lied. Okay, so, and then if you'll notice, when x is 0, that means y is 2, and that means that t is going to equal plus or minus pi over 2. Alrighty, so since I have two versions of time, then that means that I'm going to write my two tangent equations. Alrighty, so I'm going to go to another sheet of paper. Okay, so the first thing I need to do is find my slope. So that means I need to take the derivative. So my dy dx is going to equal dy dt, and I'm going to divide by dx dt. If I take the derivative of the y thing, and I'm assuming that you still have that written down, you're going to get pi sine t, okay, because that's the derivative of cosine is a negative sign. Pi stays, okay, and I can't write, this is a t. And then my dx dt is going to be a negative pi cosine t, alrighty, and then I forgot the 2. All right. I lost my brain cells this weekend. Okay, so now let's just choose one of our times to go ahead and find our slope. So I'm going to choose when time is equal to the positive pi over 2, then my dy dx is going to equal pi times the sine of pi over 2, and then it's going to be 2 minus pi cosine pi over 2. Well, the sine of pi over 2 is 1, which is polite. Oops. I'm just going to put a positive 1. So it's going to be a positive pi. And then the cosine of pi over 2 is 0. So then this is just going to be pi over 2. So the pi over 2 is going to equal the slope of the tangent line. Okay? And then I'm going to do the same thing for the negative pi over 2. So my dy dx at that point of time is pi sine, and then I have a negative pi over 2, and then I have 2 minus pi cosine negative pi over 2. Okay, the cosine of negative pi over 2, this guy still goes to 0. This guy is a negative 1, so I'm going to have a negative pi over 2. So then all that's left to do is to write my tangent equations. And remember, the point where we're actually trying to find the lines of tangency is 0, 2. These are my two slopes. So the first one I'm going to do y minus y1 is mx minus x1. And since my slopes are the same, I'm just going to substitute them into the equation with their fun signs. So I'm going to get y minus 2 is equal to plus or minus pi over 2 times x minus 0. And then my tangent lines, so my tangent is going to be plus or minus pi over 2 times x plus 2. And I think that would be sufficient to record if we were talking about recording this in a testing type situation. All right, I have a new formula for us, which is kind of entertaining, and it's the parametric form for arc length. And way back in chapter 7, we actually talked about arc length, which was new to BC. We didn't get it in AB, but the parametric form of arc length has a couple of stipulations. It says I have to have a smooth curve, C, and then I'm going to have my set of parametrics. X is f of t, y is g of t. Okay, C doesn't intersect on itself in an interval. So C doesn't intersect on itself in an interval. Oops, I spelled it wrong. Alrighty, so unlike the problem we just did where I had a loop, this one, it's okay if it has a loop, but not in the interval that we're trying to find the arc length. And then that says our interval is going to be a is less than or equal to t, less than or equal to b. Okay, it's okay if it loops at the end point. Okay, so here is our handy-dandy formula for arc length, and it looks horrible. So S is going to be the integral from A to B, the square root of dx dt quantity squared plus dy dt quantity squared dt. And it's actually really not that bad. So I would take the derivative of my x thing and square it, and then I would take the derivative of my y thing and square it, take the square root of that to be able to talk about my length. Remember that we square things to keep distances positive, and then I would be done. All right, so now that you have that, I have pre-written down an example for us, or a diagrammer, and I wrote it down ahead of time because it was just long. So it says that I have a circle of radius 1. So here's my little circle. This is the one of radius 1, rolls along the circumference of a larger circle of radius 4. And this guy is called an epicycloid. And an epicycloid is, if we just stop and digress for a moment, is when instead of having a circle rolling along, because remember we had a circle rolling along in the past, and so what it ended up doing was something like this, okay? An epicycloid means that I have a circle rolling along a circle, and it makes a lovely little flower, okay? This defines our circle. It says find the distance traveled by the point in one complete trip around the larger circle. Alrighty, so a couple of things to note is that for my epicycloid, which is the flower dude, I have sharp points at t is equal to 0 and t is equal to pi over 2. Another thing to note is that dx dt and dy dt are not simultaneously 0. Okay, they're not simultaneously 0, which means that I have a nice smooth curve. Okay, the other thing that you're going to notice, and here's how we're going to manage the problem, is this particular arc is a quarter of a circle, so, or a quarter of the pattern. So we're going to take our arc length formula, and remember it's the integral from a to b, square root of dx over dt squared, and then my dy over dt squared dt. And since this has 4 iterations, I'm going to put a 4 here, and I'm going to integrate from 0 to pi over 2. Whew, love my grandchildren, but they always make me sick. Alrighty. So now let's start managing our math, okay? So my curve is right there. So my dx dt. If I take the derivative of the x thing, it's going to be a negative 5 sine of t, and then plus, and then I have the chain rule going on here, so I'm going to write 5 times sine of 5t, okay? And then my dy dx, my dy dt is the derivative of the y component, so that's going to be, did I write that down wrong? No, I didn't. Sorry. My dy dt is going to be 5 cosine t, and then minus 5 cosine 5t. Oops, there's a little 5 in there. And again, because this is the chain rule. Alrighty, so I have everything I need. I will tell you that the algebra on this one is a little bit gruesome. I had to run through it a couple of times to get all my ducks in a row. Alright, so let's just start. So I'm going to have 4 times the integral from 0 to pi over 2. And I'm going to make my square root big. Okay, my dx/dt is a negative 5 sine t plus 5 sine 5t. And I know you can tell already this is going to get hairy. Okay, and then I'm going to have plus my dy dt 5 cosine t minus 5 cosine 5t squared, and then all outside that dt. Whew. Alrighty, so to make life a little bit simpler, although it doesn't look simpler, I'm going to square both of these because then I can combine like terms using some of my trig identities. So the 4 is going to stay outside. 0 to pi over 2 is going to stay. Alright, so if I square the first term, 25 sine squared t, multiply these two guys together and double it, so negative 25 times 2 minus 50 sine t sine 5t. Remember, these little guys aren't the same, so I can't put them together, plus 25 sine squared 5t. Ugh, that's just so gross. And then square this guy, so plus 25 cosine squared t minus 50 cosine t cosine 5t, I told you it was ugly, plus 25 cosine squared 5t, parentheses, dt, and all of this stuff, all of this stuff, all of this stuff is under the square root. All right, so at this point, I'm going to group, and I'm going to underline them a little bit. This is my square root sign, by the way. I'm going to put this one together and this one together, and then I'm going to put this one together and this one together, and then I'm going to put this one and this one together, and then we're going to do some trig identities. Alrighty, so, and then I'm going to die. Alright, so from 0 to pi over 2, here's my square root. Whew. Alright, so I have in the red, maybe I'll do it like this. I'm going to factor out a 25, and I have sine squared t plus cosine squared t. Okay, and then I'm going to do plus 25 times sine squared 5t plus cosine squared 5t. And then, what's my next one? Okay, I'm going to have to go to another page. Sorry. Maybe I'll see if I can keep that there so you can see it. All right, so I'm still all under the radical, by the way. And then I'm going to take out a negative 50, and I'm going to have sine t sine 5t minus cosine t cosine 5t. Alrighty? Whew. And that's still all under the square root dt. How much do you love me? Alright. So it's actually starting to look a little better. This guy is 1. This guy is 1. Okay. No, that one's gross, but that one's also 1. Okay. So now I have a 25 that I can factor out because I need to do that so I can get it outside the radical. So here's the 4, and then I have the integral pi over 2, and I'm just going to leave my square root for right now. So I took out, this is 1 and this is 1 because these are the Pythagorean identities. So I factored out a 25 and I got 1 plus 1. And then I'm going to factor out the 25 of that. I'm going to get minus 2 times sine t sine 5t minus the cosine of t. And I took out the 25, that guy stays, cosine 5t. Alrighty. I took out a negative, that should have been a plus, this is a plus. Whew. Alrighty. So far so good? And remember, all this is still under that thing. There's my dt. This guy can come out now, which is polite. So then I have 4 times 5 integral, that's a times, 0 to pi over 2. And then I have the square root of 2 minus 2 times the sine of t sine of 5t plus the cosine of t cosine of 5t. I know that still really looks gross, okay? All right, let me turn my page so I don't screw that up. And I'm just checking my work. So the interesting thing is, at this point, I'm going to tell you that you need to make a leap of trig identity faith. So we're going to make a leap of faith, and we're going to get that this is 20 times the integral from 0 to pi over 2 of the square root of 2 minus 2 cosine 4t and then dt. That was pretty entertaining, and it's actually one of the sums, so it's not horrible. But I'm going to ask you to make another leap of trig faith, and so this is going to be 20 and the integral from 0 to pi over 2, and the square root of this guy is going to be the sine of 2t dt, okay? So then this is a negative 20, and I'm going to have cosine of 2t evaluated from 0 to pi over 2. Whew! And we're almost done. The cosine of pi over 2 is 1. Or sorry, the cosine of pi, because the pi over 2's are going to cancel, is a negative 1. So this becomes 40, and there is your arc length. Holy cow. So my arc length is 40. That's amazing. So that was some entertaining math. Alrighty, my lovelies. That is it for you today. Again, I apologize for sounding like a frog. I will see you.